In order to study how action potentials are generated, we will first insert two electrodes into the neuron, one to record the membrane voltage and another to inject current that can be used to push the membrane voltage toward more positive or depolarizing, or more negative or hyperpolarizing voltages. Let's look at what happens when our model neuron is stimulated. The first two stimuli shown here are insufficient to depolarize the membrane past the threshold level. Thus, no action potential is generated and the voltage quickly returns to the resting level. However, the final stimulus is large enough to generate an action potential. In this experiment, the current injected into the cell, the stimulus, is represented in the upper graph, and the voltage response below. Notice that a hyperpolarizing current drives the membrane potential in a negative direction, with the voltage response of the cell directly proportional to the magnitude of the injected current. The same relationship is true for small injections of depolarizing current. The voltage response of the cell is directly proportional to the magnitude of the injected current. If the stimulus is sufficient to push the membrane potential past the firing threshold for the neuron, such as the second stimulus in this example, then an action potential is generated. Depolarization of the membrane past threshold sets in motion changes in membrane conductances that eventually leads to generation of the action potential. Note that the action potential is an all or none event. Once generated, its amplitude does not vary as a function of the size of the preceding stimulus. Any suprathreshold stimulus will produce an action potential of similar amplitude and duration. The action potential can be divided into 6 phases: an initial steady state or resting phase, a rising phase, the overshoot phase, the falling phase, the undershoot phase, and the recovery phase. We'll now examine each of these phases in turn. When a neuron is at rest, only the so-called leak potassium channels are open, establishing the resting potential. These potassium channels, a subset of all potassium channels, are constantly in the open state. During the rising phase, the increasing positive shift in membrane potential is driven by the opening of progressively more and more voltage-gated sodium channels and the entry of sodium ions into the neuron. This inward sodium current depolarizes the membrane voltage, as indicated by the red color shift in the membrane. The membrane potential is now at its most positive state. It is overshot 0 millivolts. At this positive potential, two processes are occurring simultaneously. First, the voltage-gated sodium channels that initially activated during the rising phase begin to close. As a result, sodium conductance starts to decline. Next, potassium channels begin to open, driving the membrane potential back toward the equilibrium potential for potassium. These voltage-gated potassium channels differ from leak potassium channels in that they are normally closed at the resting potential but open in response to depolarization, thus the term voltage-gated. Now, the action potential is in its repolarizing phase, i.e., the membrane potential is rapidly returning to the resting potential. During the falling phase, activation of voltage-gated potassium channels is at maximum, and the number of open sodium channels is dramatically reduced. At this stage, the action potential repolarizes beyond the resting membrane voltage. This hyperpolarization is indicated by the blue color of the membrane. The undershoot occurs because most voltage-gated potassium channels are still open, such that the total potassium conductance of the neuron is greater than when the membrane is at its resting steady state. During the recovery phase, the membrane potential returns to the original steady-state resting potential. This occurs as the delayed potassium channels that were open during the action potential now close. The membrane potential is now determined by the other channels normally open at the resting potential. In fact, the transition between the phases of the action potential is seamless, and one stage grades smoothly into the next.